So now that we know that absolute and conditional convergence can be applied to series with mixed signs, which alternating series is a type of a mixed sign series, then we want to be able to test that. Okay, so here we have our first alternating series, because of course this whole thing would be only something you worry about for an alternating series. So step one, we want to check for absolute convergence. Let's see if we can get absolute convergence, because if we can, then we're done and we don't have to do anything more, because absolute convergent means convergent. Wonderful. All right. Check for absolute convergence. Convergent. I should put a CE on that. All right. So we want to take the absolute value of this series. So let's take the absolute value, which would mean we get rid of the whole negative 1k plus 1 business. So that would mean 1 over the square root of k, which is 1 over k to the 1/2. That's divergent. That's a divergent p-series. Those p-series, man, you really got to know them. It's a p-series where the p is equal to 1/2 and 1/2 is less than 1. Therefore, it's a divergent p-series. All right. Wonderful. So we're going to have to keep going. Step 2, we need to check for conditional convergence. And the way we do that is with the alternating series test, because the absolute one isn't alternating anymore. So the alternating series test, alternating series test. Okay, well, we learned it in this section, so there must have been a reason. Step 1, we need to prove that our terms of our series are non-increasing and positive, and we need to find that the limit is equal to 0. All right, so we find the terms are non-increasing and positive by drawing a graph of the thing. So let's grab a graph. Right here. Hey, we already did this one. Okay, so we will draw a sketch of that picture with, of course, some scale in there. So it goes from 0 to 80 and 0 to about 0.6. And lo and behold, it is positive because it's always above the x-axis, and it is decreasing. So this is positive, and I should say non-increasing. Decreasing is the most common form of that, but technically it's non-increasing. All right, so that's part A, right, 2A. 2B is we want to find the limit as k goes to infinity of a sub k, which would be the limit as k goes to infinity of 1 over k to the 1/2. Well, that's 1 over infinity. I mean, I don't care. It's the square root of infinity. It's still infinity. So this would be 1 over the square root of infinity, which is 1 over infinity, which is 0. We all loved the Calc 2, or excuse me, Calc 1. So therefore, these two pieces put together mean that the series, right? Oh, this converges by the alternating series test. So therefore, negative 1 to the k plus 1 over the square root of k converges conditionally. And converges on condition that we're alternating. If we're not alternating, it diverges. That's what this part proved. That's a conditional convergence. Diverges when it's positive, converges when it's alternating. All right, so let's do to the next one. All right, negative 1 to the n plus 2 over n to the 5th. Okay, well, let's check for absolute convergence. I have a little bit of room here. Which would be step 1. But if we can prove it, then that's all we have to do, which is always nice. All right, so let's see here. If I take the absolute value of b sub n, because it's letter b, get it? That would be equal to, okay, so if you're taking the absolute value, it's going to make the negative 1 to the power part disappear. So it's going to be 1 over n to the 5th. that converges. That's a convergent p-series. Convergent p-series. P-series converge when the power is greater than 1 and 5 is greater than 1. Okay, therefore we're done. Once it converges absolutely, that's the more powerful convergence anyway. So we'll just say -1 to the n plus 2 over n to the 5th. Oh, except my 5 looks like a blob. Sorry about that. Oh, now it looks even worse. Hold on. There we go. I'm not sure that's better, but converges absolutely. All right. Now, this one's a little bit strange. We might kind of want to note what's going on here. So, if you'll notice, the sign of n is a weird term. We haven't seen that before. We've seen something similar to it. We saw the cosine of n pi, but there's no pi in this, right? Cosine of n pi is +1 minus 1 plus 1 minus 1. But this isn't that. This could be a decimal, right? I mean, the sine of 2 is not anything we really know. So, but we do know that -1 is less than or equal to the sine of n, which is less than or equal to 1. It has to be, right? Because sine is a wave function that's always between -1 and 1. So wherever the sine of n is, it's going to hop around between positive and negative symbols, but it won't be 1 and -1. Interesting. Now this is why we say the term mixed sign. Did you notice that? It might have slipped by you without any kind of big deal. But that's why we say mixed sign. Alternating is a special kind of mixed sign. Alternating is like +1 minus 1 +1 minus 1, or like +1 +1 minus 1 minus 1 +1 +1 minus 1 minus 1. Mixed sign means it's just doing positives and negatives, but they're not necessarily ones. They could be kind of all sorts of things, which was what would happen here. These would actually all be decimals, but they'll be decimals that are positive and negative. Interesting. Okay, so that's going to make proving convergence a little bit different. It's not just going to be a straight p-series like it was in the last one, but it's going to be close. All right, so let's prove or check. Hint, it's going to be absolute convergence, so that's nice for us. Checks for absolute convergence. All right, so if we take the absolute value of c sub n, get it? C, letter C for this problem. All right, so C sub n, that would be equal to the absolute value of sine of n over n cubed. But see, n is already positive anyway, so the denominator part on that doesn't really matter. So we can just say that sine of n, that part needs to be in absolute values because that could go negative. But over n cubed, that's never going to be negative, so I don't need to worry about it. So I need to prove that this is convergent, and it is. Because if you notice, this is always less than 1, right? Less than or equal to 1. Okay, so that means that this numerator is always less than or equal to 1 over n cubed. But 1 over n cubed is a convergent p-series. Right? Because p is 3, which is greater than 1. What am I doing? That's a comparison test. Remember comparison tests from a previous section? So we just proved that this, right, that's a comparison test right here. Not a limit comparison, just a direct comparison. Because, I mean, it's so obvious. The absolute value of sine of n is always less than 1. So this is, you just strip that away, make it a 1, and ta-da. That one's convergent, therefore this one converges also. I just went to grab the convergence test here, right? We have one series that's always less than another one, and the bigger one converges, therefore the smaller one does too. That's what we just used. So this blue one is always less than that orange one, and the orange one converges, therefore so does the original. Lovely. And that means that this is absolutely convergent because we just did it. The absolute value converges. So therefore the series converges. So that means that Cn converges by the comparison test, right? That's what we just proved, right? So this bit converges by the comparison test, and therefore our original series, which was sine of n over n cubed converges absolutely, because the absolute value converges by the comparison test absolutely. Therefore, the part when it's alternating, or with mixed signs, I should say, the mixed sign portion also converges. All right, last one. So we have negative 1 to the k over k, or excuse me, times k over k plus 1. And just knowing what I know about series, I think we're in trouble. But I'm going to prove why that trouble matters so much. Okay, so step 1, I would want to check for absolute convergence. I'm not going to get it, but I'm not going to get it in a particular way. Absolute convergence. Okay. So if I look at that series, which is d sub n, get it, letter D. So the absolute value of d sub n would be getting rid of the negative 1 to the k part, and would leave k over k plus 1. And hopefully little alarm bells are going off in your head, because that's not good, right? The limit as k goes to infinity of k over k plus 1 is... that's infinity over infinity. So technically, by L'Hopital's rule, we know that it's the limit as k goes to infinity of 1 over 1, which is 1. And you know what 1 is? 1 is not 0. Right? You can use L'Hopital's rule, or technically it's a rational function, so we can use that little table that we learned in section 10.2, right? That if it's a polynomial over a polynomial, you can take the ratio of the leading coefficients, which in this case is 1 and 1, therefore it's 1. Okay, so what is this? What do we just do? This sucker just failed the divergence test, right? So that's the divergence test, and we failed it. Well, I guess we passed it. We're divergent, right? So that means that the absolute value of dn, dk, sorry, this was a dk. K was my letter here. So dk is divergent. By the divergence test. Oh, okay. But the divergence test is a problem for us. I mean, it's not a problem, but it's going to mean something. So if you look at the alternating series test, if you remember, I got to go back to the beginning of this section to the alternating series test. If your limit of your terms is not 0, you are divergent. Right? So if you fail from the divergence test for part A, then you're divergent for part B, right? There's no getting out of this. So you can, if you fail the divergence test, that also means, but that means that the series dk also is divergent. Because failing the divergence test means you fail part 2 of the alternating series test. And we're done, right? Our series is divergent. Now, I know what you're thinking. You're thinking, well, okay, why don't I just do that all the time, right? If it fails, then it fails and we're done. Nah, because it's possible to have a series that is divergent here for other reasons, right? You can have a series that diverges but would pass the alternating series test, and therefore it's conditionally convergent. It happened right here, and it happens with the harmonic series, right? The harmonic series is divergent when it's absolute value, but it converges when it's alternating series, right? So you can't rely on that. But the trick is that if it fails because of the divergence test, right, not because of some other reason, say it's like a p-series, right? So if it fails because of the divergence test, then it fails, right? So once you fail by the divergence test for this part, then that means that it's all automatically divergent for the alternating series part, and you're done, right? Once this part is divergent due to the divergence test, not for other reasons, then you can just be finished and write this. Basically say, yep, it's going to fail the divergence test, or excuse me, because it failed the divergence test, it will also fail the alternating series test, and we're done. So both parts are divergent. The absolute value diverges, and the regular part, without the absolute value, the mixed sign part, also diverges. But keep in mind, you can diverge for other reasons, in which case then you do have to do all the rest of this. But if this had failed the divergence, first, if this would have been divergent because of the divergence test, we wouldn't have had to do all of this, because then you automatically fail part B and you're done.